Okay, the third session on probability, we're going to look at what's called the normal distribution. So in doing that, we'll consider these following topics. We'll have an introduction to the standard normal distribution. We'll look at standardizing the curve and what's called the normal standard variant Z. And then we'll look at determining probability from the normal distribution. Okay, so what this is around is us being able to predict how many people will fall in a certain, for instance, we'll be looking at an example problem that is around people's heights and how many people fall so far away from the mean. All will become clear as we go along. So, introduction to the standard normal distribution. Okay, well, if you look, we've got a curve on the right, figure 1. Okay, typical normal distribution curve. So it starts off low, goes up to a peak, and then falls away to almost nothing again. Commonly called the bell curve because it looks a little bit like a bell upside down. Okay, so it's an extremely important one, and you can expect this kind of distribution to be produced when a data sample is very large. You know, we're talking maybe at least hundreds, if not thousands of data points taken, so that you get a really good idea of the average, and that will normalize into this kind of standard curve. For example, the results from GCSE maths over the whole country, they would fit that when they're doing results to a standardized normal curve. And that's the way, I don't know exactly how they do it, but that's the way they make sure that different exam papers over different years give the same standard of results for a particular grade, for example. So it can be described by a mathematical equation. We'll look at that quickly, but you're not expected to use it on this course and at this level. And is the basis of much work in advanced statistics. Many natural occurrences, such as the heights and weights of a group of people, the sizes of components produced by a machine, and the life length of certain components approximate to this normal distribution. So what this is saying is if you take enough samples, eventually if you plot them all, you'll get a distribution curve that looks something like this bell curve. Okay, it might be skewed over one way a little bit sometimes, or the other way, but that's the kind of shape that you'll get pre-standardized. Everyone happy with that?
Yeah, fine, Mike.
Right, so normal distribution curves can differ from one another in 4 ways. By having different mean values. So you could sample 1,000 people one day and sample a different 1,000 people another day, and the mean is likely to be different. Yeah, for example, they can have different values of standard deviation. So you might get a sample that's really spread, and the standard deviation is quite high. You can get another sample where the standard deviation is quite low and the sample's not that spread. The variables having different values and different units, so they can be different in that respect, and there can be different areas between the curve and the horizontal axis. So what we're saying there is we could have, because a lot of this we're going to do is about the area underneath the curve. We could have a normal distribution like so. Equally, we could have quite a tall distribution where the area under the second one is much bigger than the area under the first. Okay? Yeah. Everybody happy with that? No dissenting voices. I will move on. Okay, so what we have to do before we can use this is have to do what's called standardizing the curve and look at the normal standard variate that's called Z. All right, so normal curve is standardized as follows. The mean value of the unstandardized curve is made the origin. This makes the mean value of the x equal to 0. So what we're saying is on this bottom scale down here, we're measuring how many standard deviations we are away from the mean. So this is, if this is the mean value, let's say that's mean value of a heighted group of people is 1.6 meters. Yeah. Anyone over this way is taller, higher than 1.6, and any data over this side, for instance here, lower than 1.6. Yeah. And the measure is how many standard deviations, remember we calculated standard deviation last week, are you away from that center? All right. So the horizontal axis is calibrated in standard deviations. This is done by letting Z equal x minus x bar over the standard deviation. That's where Z is the normal standard variate, x is the value of the variable, and x bar is the mean value of the distribution, with sigma being the standard deviation. So there's a lot of information there, okay? But what we do when we take a look at an example, we'll calculate the Z value, and then we'll use a table to find out what the probability is. And that's actually quite an easy process to go through. All right, but understanding how it works is just a little bit more difficult. Okay, now the last thing about the standardized curve is the area beneath the curve, the area between the normal curve and the horizontal axis is made to be equal to unity. Remember, we always have this with probabilities, that all the probabilities add up to 1. Yeah. So that area marked out in red is set to be equal to 1. And it was representing all the possible probabilities that we could have, and they all add up to 1. I understand that's a little bit opaque at the moment in terms of you haven't done an example, but do you all kind of get where I'm coming from with that? The idea, if we want to find a Z value, and that's here somewhere, and that's height is equal to, I don't know, 1.8 meters, X would be 1.8. X bar would be the mean, which we said is 1.6. Okay, and then so we'd do 1.8 minus 1.6 over what the standard deviation was. I don't know, let's say that was 0.2. We do that calculation, that would give us a Z value. All right, and the Z value is a multiple of standard deviations. Everybody happy for me to move on and get it into more of a specific example? Good. Right, so determining the probability from that normal distribution. Right, if we look at the diagram on the right, we got a Z1 that's below the mean and a Z2 that's above the mean. And that area is indicating between Z1 and Z2 standard deviations of the mean. So that area would give you the probability or the number of data items that would fall between the Z1 and the Z2 values. So when a normal distribution curve has been standardized, the normal curve is called a standardized normal curve or normal probability curve. And any normal distributed data may be represented the same normal curve. Now we find the area under the normal distributed probability curve is directly proportional to the shaded area shown in the diagram, which I've already said. Okay, so the probability is proportional to that area. It's found using this formula here. This one. Hang on. Let's pick this up. Highlight this formula. Now, that formula is involving some calculus that you haven't studied yet, but you are going to in Learning Outcome 4. Okay. But this is the symbol for finding the area beneath a curve. It's integrating, which you'll learn how to do that. You might not learn how to integrate that one, but you will. And that's where the value of Z is as the formula we showed before. However, in order for you to save you repeatedly determining the values of this function, tables of partial areas are included in many mathematical formula books, and such a table is included on the next page. So if you've looked ahead, you'll have seen these. But this is a table to help you find, for a given Z value, what the probability is. So, for example, if we had a Z equal to 1.00, that would come here. And the probability is equal to 0.3413 from the table. So once you've calculated your Z value, all you need to do is come to this table and find the appropriate probability for that Z value. Yeah. Okay. If I had Z is equal to 0.62, I'd come down here, I'd look for 0.6, I'd go across to 2, and that's 0.2324. So that's not particularly difficult. That's a lot easier than using that formula, let me tell you. Okay? You're all fairly happy with that. No dissenting voices. Right, let's have a look at a proper example then. The mean height of 500 people is 170 centimeters. So mean X bar equals 170 centimeters. The standard deviation is 9 centimeters. So sigma is 9 centimeters. Assuming the heights are normally distributed, determine the number of people likely to have heights between 150 and 195 centimeters. Now, it's always useful to sketch this normalized curve and just confirm in your mind what we're looking at here. So here's a normalized curve that we'd expect to get from this sample. Okay. We'll put, using a different color, a line down the middle representing the mean value, which represents 170 centimeters. Yeah. And then the question saying we want to find how many people, the number of people this predicts lies between 150 centimeters and 195. Yeah. So what we'll do is we'll have two Z values, Z1 and Z2. And the probability for Z1, I'm going to do them in different colors. Just let me cross that Z2 out. Z1 will give us, when we use the table, will give us this area. Yeah. And use blue for 195 centimeters. When we use Z2, we'll get the area there. So to get the total area, we'll need to add the two values, probability values together. Okay, so I'll go back to black. I'll go to green and do Z1. Z1 is equal to, just check our formula. Formula is Z equals X minus X bar over sigma. X is, with Z1 we're talking about 150 minus X bar 170 over the standard deviation 9 equals. Put that in your calculators and see what you get. Minus 2.22.
Yeah.
Yeah. Minus 2.22. Value in table for minus 2.22 is, so we go back to our table. We forget about the minus for a minute, because all that's indicating is us below 2.22 there, 0.4868. Yeah. 0.4868. So that's the probability that something will be between the mean 170 and the X value 150. All right, so that's the Z1.
How did you decide which along the top, the 0, 1,
What
2,
you
3,
do
4, 5?
on the table, the first two digits are down the left. Yeah, so we're looking for 2.22. So the first two digits are here.
Yeah.
Yeah, and the third digit is up the top.
Oh, right. Okay.
Yeah. So you've got 2.2 on the end, and then the first number is 0.220, then 0.221, 0.222, and so on across from left to right. All right. Change the blue. To get the blue area, we need Z2, and that's equal to, and the value we're looking at is 195 minus 170, again over 9, and see what we get. Two point seven, 2.78.
Yeah, I got 2.7 reoccurring. Would you take that as 2.78?
Yeah, because reoccurring means 2.77. So you'd 2.777, therefore you'd round up the third digit to 8. Yeah. And again, we go to the table and we look for 2.7. There's 2.7 in that line, and 8 there. 0.4973. 0.4973.
Mike, this might be a silly question, but you can't have minuses in probability, can you?
Oh,
Just for
hang
the
on, just let me write this, James, and I'll explain it. For 2.78 is 0.4, what did I say it was? 973. The Z1 comes out with negative, James.
Yep.
Because it's to the left of the mean. It's lower
Sure.
than the mean. Yeah. But
Yep.
in terms of finding the value in the table, the probability in the table, it doesn't matter whether it's positive or negative.
So you wouldn't have to
Because-
write a minus, you'd just write the
No,
0.4868.
that's right.
Okay, no problem.
But that's the probability of a person's height being between 150
I
and
understand that.
170, which is lower than the mean.
Yeah, okay.
And then the other one is between 170, sorry, 195, which is above the mean.
Yeah.
To
No
get
problem.
to get the number of people that lie in the whole lot between 150 and 195, we've got to add the two probabilities together. Yeah.
Because it's two separate parts. So to make the whole, you have to
Yeah.
add them together. I get that. Yeah, that's fine.
These two probabilities here, that one gives you the probability of lying in the green bit.
Yep.
This one gives you the probability of it lying in the blue bit. So to get the probability of them lying in both bits
From
combined.
151 to 195, you have to plus the two together to get the whole area.
Yes, that's
No
right.
problem.
Yeah.
Cheers, Mike.
So we can write down here probability between 150 and 195 equals 0.4868 plus 0.4973 equals 0.9841. Yeah. Therefore, number of people between 150 and 195 centimeters equals 0.9841 times the number of people in the sample, which is 500. $492 to the nearest person. Okay. All happy with that? Yeah, you must get this thing that any one Z value gives you a probability between the mean line and either above or below. So if you want, if your sample is crossing the mean line, then you have to add the two together. Yeah.
Mike, can you just explain where you got that 500 from at the bottom? I was writing.
The 500 comes from the mean, because the sample has a mean height of 500 people.
Okay, yeah. Thank you.
So the problem, you get this probability will tell us if we standardize that curve and look at the probability of the two heights, 159, 195, that will give us statistically that there is 492 people between those heights, and all the others, the other 8, fall either taller than 195 or shorter than 150. Statistically.
And that'll be shown on the ends of the graph. So the 8 people.
Yeah, there'll be these two little areas on the ends. Yeah.
Okay, no problem.
Will that always be a whole number? Because obviously you've got a student can't be a half or anything.
Well, no. I mean, that depends on what your data is, doesn't it? I mean, because we're talking about people here, we can't have what's effectively a 20th of a person. So you'd normally go to the nearest person in this kind of thing.
Okay.
But quite often, I mean, relatively, 500 people is a small sample when you're doing something like this. And you do need big samples, because otherwise you're making a lot of assumptions that can't be true. So it works on big samples. From 500 is relatively small. All right. Yeah, you must remember that it's not, there are 492 people. That means on the data we've got, statistically, there's 492 people. Yep. So on the next page in your notes, I've properly highlighted those two Z values that we've just picked out. So the 2.22 standard deviations and the 0.278 standard deviations. All right. And actually, if you look at this table, if we look at 2, that's 0.4772. If we add that together, we get 0.9 something, and that's actually about 92% on a standardized curve, will fall between two standard deviations of the mean. And if you go up to 4 standard deviations of the mean, you end up catching everybody statistically. All right. So that's one example. Let's have a look at a slightly different one. For the group of people given in problem 1, yeah, so we've got the same group of people. So it's 500 sample. Mean was 170, and standard deviation was 9. Yeah, so for the same group of people, find the number of people likely to have heights of less than 165 centimeters. Okay, again, I'm going to draw the sketch because I think it helps, and I do recommend that you put sketches in your assignment answers. I don't want that, do I? I want the horizontal. There's our horizontal line. There's our normal curve. Yeah. We've got a mean here equal to 170. Yeah. And we got a line in here. Color, let's make it green. .165. Yeah. We're interested in this area. Lower than, less than 165. All right. But our Z value, remember, will give us this area. From what I've told you about the standardization of this curve, without looking back, what is the whole green and red area? What's the value of that probability-wise?
Is it a half?
5.
It is half. It's 0. Remember we said under the whole bell curve, there's 1. So under half of it must be 0.5. So what we've got to do here is find this red area and take it away from 0.5 to give us the green area. Yeah. So first thing we need to do is find Z. It's our value, 165. Take away our mean, 170. Divide by the standard deviation 9. I get 0.556. 0.56, so 3 digits. Minus actually, because it's underneath. Yeah. So then we go and look at our table for 0.56. 0.56. There's a 0.5 line. Here's the 6. 0.2123. So the probability for Z equal to minus 0.56 is 0.2123. Yeah. So probability of less than 165 centimeters equals 0.5 minus 0.2123. So we're taking the red bit away from the whole area of the left-hand side equals 0.2877. So that represents the green bit. Let's highlight that in green. That represents the green area. Yeah. So therefore, number of people less than 165 centimeters in height is 500 times 0.2877. $143.8, so it's 144 to the nearest person. So statistically, this sample is saying that out of 500 people in that data, with the data given, 144 of them are less than 1.65 centimeters tall. Okay with that, everyone? Aye or nay?
Yeah.
Yeah, fine,
Yeah.
Mike.
Good, good. I'm just going to put my light on, I can't see very well now. Right. So we'll look at the next page, see what we've got. For the group of people given in problem 1, find how many people are likely to have heights of more than 194 centimeters. So have a go at that one. That's the opposite to what we've just done. We're just like we just did, but we're on the right of the mean. So sketch out the little bell curve and find your Z value for 194. And remember that you're going to have to take that Z value away from the 0.5 to get all the people above 194 centimeters. Okay, just for the video, summarizing the problem 3, group of people given in problem 1, find how many people are likely to have heights of more than 194 centimeters. So the mean was the same as before, 170. Standard deviation is 9 centimeters. We're looking for this blue area over to the right of 194. So if we find the area here between 170 and 194 and take it away from the whole half area there, we'll get the probability of falling taller than 194. So the first thing we do is find the Z value. There's 194, take away the mean 170, and divide by the standard deviation, we get a Z value of 2.67. If you look in the table, the Z values, for Z value 2.67, the probability is 0.4962. Therefore, the probability of people above 0.4962 is the half, which is the whole area to the right of the mean, take away 0.4962, leaving 0.0038. Therefore, the number of people taller than 194 centimeters is 0.0038 times the 500, 1.9, or to the nearest person, 2 people. So statistically, in that sample, you'd expect to find 2 people taller than 194 centimeters. Right, so we're looking out of the 1,500 bottles for how many of them are less than 750 ml. So we're looking at a situation where we've got a normalized curve, yeah, where the mean is 753, yeah, and the standard deviation is 1.8. And this part of the question is saying how many does this predict are less than 750? So we're looking at this green area down here. Yeah. If you're doing a sketch, that's what you should have. Yeah. So what we're going to find using the Z value is the red area. And then we'll take that away from 0.5 to get our answer. So what answers have we got for this question? How many bottles?
What, the actual answer?
Yep.
I got 71.
Anyone else get 71?
I got 72.
Okay, so that could be a rounding thing somewhere. Yeah. 71 is what we should have, because our Z value is X, the 750, minus the 753 over 1.8 equals minus 1.67.
That's where I've gone wrong. I rounded it down for some reason for 166.
Yeah, if a 6 reoccurring, then that'll be minus 1.6666 forever. Yeah.
Yeah,
If you want it to
I
3 places, then this one rounds up to 7. All right.
Yeah, I think I just rushed.
That's okay, but you do have to be careful, because you saw in that other problem how that can make quite a big difference in these
Yeah,
calculations.
well, I'm one bottle out, aren't I? So it's not right.
Yeah. For Z equals minus 1.67, probability equals, from the table, 0.4525. Therefore, probability of less than 750 ml is the 0.5 minus 0.4525 equals 0.0475. Therefore, number of bottles less than 750 ml equals 0.0475 times the 1500 in the sample equals 71 to the nearest bottle. Yeah. So that's that problem. Because we were looking for a less than, that's going to be to the right, and we're going to find between that less than and the half and the center line and take it away from half to find that green area. All okay with that? Good. No dissenting voices. So what we're then, the next question asks us to determine how many bottles lie between 751 and 754. So in this problem, there's our mean, 753. We're interested in the 2 values, the one in red 754. And the other one in green, 751. So this time, if we want all the bottles between those two values, we've got to find the two separate probabilities, i.e. the two separate areas, and then add those two areas together and multiply by 1500. So if we call that one Z2 and the green one Z1, yeah. Z1 is the value 751 minus the mean 753 over 1.8 equals minus 1.11. Everybody get that? And Z2, please shout if you're not getting this. Z2 is 754 minus 753 over 1.8, which is 0.56. The values in the table are for minus 1.11, they are 0.3655 and 0.2123. Yep. Therefore, probability of contents between 751 and 754 ml equals 0.3665 plus 0.2123, because we want the area between the two, so they added together, equals 0.5788. Therefore, number of bottles equals 0.5788 times 1500. What you got? 868. 868 bottles to the nearest bottle. Okay. Anyone got any issues understanding how that was worked? The green area gives the number of bottles between 751 and 753, and the red area gives the number of bottles between 753 and 754. So to get between the two outsides, you add them both together. Okay. Part C. What results have we got for part C? Contents of more than 757. What kind of answers have we got?
Could you just quickly go back to the last page, Mike, for me?
Yeah, I can.
Yeah, done.
All right.
Yeah.
That was very quick.
Yeah,
So,
I literally just missed the very last bit. I was trying to write it all down, and I had internet problems, so couldn't see the start of the class. So I'm trying to catch up and work it out, but I just missed it.
so here's our curve again. There's our mean, 753. We're interested in greater than 757, which is this blue area here. So again, what we're going to do is find the red area and take it away from the 0.5 to get the blue area. Yeah. So the Z value is our 757 minus the 753 over 1.8 equals. You got 2.22, anyone?
Yep.
Yep. Value in table equals 0.4868. Yep. Therefore, probability greater than 757 ml equals 0.5 minus 0.4868, because we're interested in the blue bit on the end, equals 0.0132. Therefore, number of bottles equals 0.0132 times 1500 equals 20. Bottles. All happy with that?
Yep.
Yep.
Yeah. Now, this last one, it's a little bit tricky, and the diagram
Sorry.
will definitely. Go on.
Mike, could you just very quickly?
Yeah.
Yeah, all good. Done again.
Yeah. Sorry, Solly.
No worries.
Right. The last one's a little bit tricky, and a diagram showing what you're trying to do be really helpful here, and it might even be helpful to split it up even further. Here's our overall bell curve. Our mean still 753, but we're interested in, in red, we're interested in the area between 750 and 751. Yeah. Now, we know what the whole area to the left of 753 is worth. It's worth 0.5. And we know how to find this green area here. Yep, we can do that. And we know how to find the blue area. Don't we? And the bit we're interested in is the bit between those two, isn't it? It's this bit in here that I'm going to highlight in pink. That bit. Yeah. So if we find the green and the blue, add them together and take them away from the 0.5, we'll have the value between the two. Can you all see that?
Mike, can you do that the same with 753 and 752, and then 753 and 750, and then like minus the one from the other.
Yeah, what you're going to do, the green area is fairly easy. That's a straight area between 752 and 753. Yeah.
Yeah.
Then you'll find the blue area by finding the area between 750 and 753 and taking it away from 0.5.
Yeah. Okay.
That'll give you the blue and the green. If you then add the blue and the green together, you'll have the total area of those two. And then if you take that away from the 0.5, you'll have the little bit left in the middle.
Right. Okay. Thank you.
So effectively, you're going to find, I'll do it in two diagrams. You're going to find the red area first. Sorry, the green area. That one. Yeah. You're going to separately find as you mean this blue area up here, right? And then the purple bit is the bit in between the two. Yeah. Does that help or not?
Yeah, that's fine, Mike. Thank you.
So, starting on that then, green area. Do it in green. It's the green area is 752. Should be 751. That should. That's one in the question. $751. That is. Yeah. The area between 751 and 753. Yeah. Z is 751 minus 753 over 1.8 equals. Actually, we've done that one before. It's minus 1.11. Yeah. Value in the table is 0.3665. So that'll give us the area of the green. Yeah. Now, the blue area is going to be 0.5 minus the area between 750 and 753. So to find the blue area, we go Z is equal to 750 minus 753 over 1.8 equals. 750 minus 753 or 1.8 equals minus 1.11. Hey? Can't be the same as the one above. Oh. Push the wrong button on the calculator.
I've got 331 minus 331.6, I think, Mike.
What, for this? For the answer to this?
Yeah.
No, it can't be that. 750 minus 753. I got 1.67
Yeah, that's what I got.
minus 1.67. You need to make sure you use your fraction button so that you've got, it does this top line, the numerator all in one go, James.
Yeah, that's what I'm doing wrong. Thank you.
Yeah, all right. Because otherwise, if you just put it in your calculator as it stand, that'll do 753 divided by 1.8 first, and then take that off 750. All right.
Yeah, thank you.
Yeah. So that's 1.67. Yeah. So table value for minus 1.67 is 0.4525. Okay. So area blue is equal to 0.5 minus that 0.525 equals 0.0475. Okay, so now we've got the blue area and the green area. Therefore, pink area equals 0.5 minus these two added together, the green and the blue. 0.0475 plus 0.3665 equals I make that 0.086. Yeah. Therefore, number of bottles equals 0.086 times 1500 equals 129. Okay, so a little bit of a tricky one, that one, and it really does need the diagram so that you can understand it. All right, so you think carefully about including or doing sketches to visualize exactly what area you're looking at, knowing that the area under the whole curve is 1, so the area under half of the curve is 0.5. And thinking carefully about which bits you're interested in and which bits you want to throw away as such, right? On the remaining page, there's 3 exercises for you to have a go at. I do strongly recommend that you have some practice and make sure that you're getting these values in the square brackets when you do your calculations. All right, So reminder of the session, we've got 15 minutes left. Have a go at one or two of them, see how you get on. Right?
Mike, could you quickly just show me